and ECoG hand pose estimation. Hello, nice to see you.
Hello, is my voice clear?
Yes, and also the video. Please click on the share screen button.
Yes.
It's loading. I can see it. Just go to full screen.
Okay, so now you can see my screen, right?
Yes, please go ahead.
So thank you for this opportunity, first of all. We also did our project on ECoG hand pose estimation, and we call ourselves PyEPosers because we did majority of stuff in Python with ECoG hand positions. So first, we really wanted to understand really what was happening in the data, like how the trials were organized. So on the right-hand side, you can see that it is showing finger number 2, like rock, paper, or scissors. So we are trying to see, okay, in the time course, how is this actually happening? So we really first wanted to understand the data structure, that there are 90 trials, and there's one subject's data, and this is how the data structure is organized. And with the help of this data, we wanted to answer the questions, okay, which channels actually matter, and how do we organize and split the data for a classification problem. So we chose a classification problem, and I'll explain about this in the next slide. So first of all, we went into a very exploratory visual analysis approach. On the right-hand side, you can see the spatial visualization, just as we got in the dataset description. Okay, how does the positioning of the electrodes actually look inside, like what is an estimate? And on the left-hand side is like the heat map of this, the distribution of the activation on these electrodes. So, and on the next slide, you can see first we wanted to understand really how do we go about preprocessing the data. We took inspiration from the paper, which mentioned a bandpass filter and a notch filter. So we used this, and we tried different types of parameters, and the configurations that we were found working well with the classification algorithms will be presented in the results section. On the left-hand bottom left, you can see that after band passing and notch filtering the data, we applied like an IIR filter, like autoregressive model. And from these, we got the parameters of the data generating process. So you can see that these two curves actually start to converge really well. This convergence tells us, okay, we have some idea about really the distribution of the data. So our classifier will learn good features. And after we did the preprocessing, it was time to do the feature engineering. So feature engineering comprised of two parts: feature reduction and feature selection. So it was more trial, error, and visual inspection. In this part, we wanted to see what are the spatial patterns and which all techniques we can use. So also which techniques work for us will be presented in the results section. And this time when we were really thinking about how do we select these parameters and how to go about it, the best idea was to see the average effect. On the right-hand side, you can see the ERPs. So we defined like 3 classes for the rock, paper, and scissors, and really tried to see the evoked potentials for rock, paper, and scissors. You can see the third one is really noisy. So we can gain an intuition that probably on the third class, we would not get such a good classification accuracy. And on the left-hand side, we show power spectral density. So here is like the average PSD from all the channels. And when we were not filtering the data properly using a notch filter or a high pass filter, there was a bump at around 50 hertz. And this parameter was also mentioned in the paper. So we got an idea, okay, that we really need to apply a notch filter around 50 hertz or something. So like this, it was like a lot of trial and error and sharing each other's code on GitHub, seeing whose parameters are working and which type of combinations really work for the best classification accuracy. And here, so we did 2 implementations. One was in Python and the other was in MATLAB. So the Python implementation was done majorly by me and Stepan. And the MATLAB implementation was done by 3 people, Vibha, Kanjar, and yes. And so we really compared what type of accuracy we got from both these approaches. And here we sort of use like ensemble modeling, in which we really try to combine as many configurations as possible of the pre-processing, feature reduction, and the classifier. The best performance that we got was for the Riemannian features and classifier. And also when we had the evoked responses, the paper also mentioned that they took like a window of 0.75 seconds on the stimulus onset to have a sliding window around this stimulus presentation. So we also use this in our model, and we tried different possibilities for this parameter, and this really worked well when we put it into cross validation, classification. And also we wanted to see, okay, how many components really works well with our type of data. And for the CSP, we got 12 components that works the best. And surprisingly, third class was the easiest to classify. So we have to see, we all were trying to see the reasons for that. And so Stefan really put different techniques, and we got really good accuracy, which can not exactly be compared to the research paper that we had, because the data we had was a little different. And from the MATLAB code, we also got these parameters. So they, Rajkumar also used common reference filter, notch filter, and bandpass signal. And you see here, he used adder boost and random forest, and the random forest really gave really good accuracy on the cross validation score. So overall, we achieved really good results for the 3-class classification problem. And we were really happy, and it was really, really good that we achieved good performance on the problem that we defined. And going to reflection first, it was really hard to think of how the data is organized and how the pre-processing actually could impact the accuracy, and what does the filtering even mean. So, but we had an idea about like generally in machine learning, you would use a lot of hyperparameter optimization and really try different techniques. That's why we worked in like as many solutions as possible and try to combine that. Initially, we got like 97.78% accuracy, but the model was overfitting. So we also had to think about, why is the model overfitting, and do we are we making some mistakes, and we want to make it more generalizable. So we tried to incorporate this in our results later on, and we did get some optimality in terms of generalizability. But obviously we had just data from one subject, so it can't be really generalizable in that sense. And last but not the least, we were always on a voice call throughout, so multiple voice calls. This is just one voice call, which lasted almost 14 hours. And we are a very diverse team, based in Germany, France, Russia, and 3 people who worked on the MATLAB code were based in Sweden. So that's about it.